Welcome to the second lesson on capital budgeting. I'm assuming you've looked at and listened to the first lesson, and I'm going to build on some of the examples from there. In this lesson, we're going to talk about internal rate of return, which is known by the acronym IRR, then something called the modified IRR, payback period, and discounted payback period. In the examples from the previous section, we evaluated the NPV of a series of cash flows against the rate of return as an alternative investment such as banknotes, stocks, or bonds. However, we did not pinpoint the exact rate of return where the NPV became zero. If you recall, we looked at several discrete rates, and I might say, well, between 4% and 5%, we went from a positive NPV to a negative, but we never actually pinpointed where the NPV became zero. So that point is known as the internal rate of return, or IRR as we'll call it here. That's the acronym. The IRR is a discount rate that makes the project's NPV equal to zero. And then we have this definition from Wikipedia, which I'll read off to you concerning the IRR. The internal rate of return, IRR, is a measure of an investment's expected future rate of return. As the IRR is an estimate of a future annual rate of return, IRR should not be confused with the actual achieved investment return of an historical investment. The term internal refers to the fact that the calculation excludes external factors such as risk-free rate, inflation, the cost of capital, or various financial risks. All right, so that's a bit abstract. I rather like my more high-level definition up here, but just to be official, I'll give you what they had from Wikipedia. I think this will become clearer, if it's not clear already, that if we look at some examples, which we're going to do. Recall from the previous lesson that NPV is given by this equation. Let me point to it. Is given by this equation here, where the C sub 0 was the initial investment. That's why it's negative. And then the C sub 1, 2, up to N, were the cash flows computed at the time of the initial investment. That's why we have this term in here. And what we want to do here to find the IRR is to set this equal to 0, and then, or equivalently, this here, just bringing this C sub 0 onto the other side, and then solving for I, which is not easy to do manually. You need an algorithm to do that, and such exist in the, for example, Microsoft Excel can do this. So in other words, we are looking for the value, and it turns out there could be more than one, and we'll get to that complication. But so we're looking for the value or values of I such that the initial investment equals the present value of the subsequent cash flows. In other words, this side here, resulting from the initial investment, C sub 0. The decision rules concerning IRR are as follows. If the IRR is greater than the cost of capital of investments of comparable risk, this is critical. You need to size up your perceived risk, or your analysis of the risk for your investment. And the example we had was the furniture company. You need to compare that to the alternative investments, and then look at your IRR. If the IRR is greater than that cost, then go ahead with the project. If the IRR is less than the cost of capital of investments of comparable risk, do not go forward with the project. In the likely event that the IRR is exactly equal to the cost of capital, then the analysis is indifferent. You can go either way. On this slide, I have the example we talked about in the previous lesson. If you recall, we had the Acme Furniture Company, and Alice and Bob were looking to do some improvements to their company. And we had this chart. It showed the semi-annual cost of capital, and we concluded that at 7%, it still had a positive NPV, but if they thought the risk was equivalent to 8%, some external investment, then it would make more sense to go with that external investment rather than invest in their furniture company, because we want negative. And at the time I said, well, somewhere between 7 and 8%, we hit zero. And that's the IRR. And so we want to compute that using the Microsoft Excel IRR function with the information from the table below. And these were the cash flows, the net cash flows. This was the initial outlay investment, so it was negative. And then these were the anticipated cash flows. They were all positive going over 6 years. They were listed in semi-annual amounts here. So we put all this information into Excel IRR function. We get a more precise value of 7.71%, which kind of makes sense. It's right. It's between these two numbers. And we could have estimated this annually. We could manually, I should say. We could have done 7.25 and 7.5 and then 7.75, and we would have seen it was between the 7.5 and the 7.75, and then we could have done some smaller increments in there, and we would have eventually gotten pretty close to this number here. So it's possible to do it manually just by doing some tests, but why not just use the more precise function from Microsoft Excel. So if the cost of capital is less than 7.71%, the Acme Furniture Company should invest in the project. If it's higher, they should not invest in the project. And again, it all depends on what Alice and Bob, the owners of this company, think the equivalent risk is. If they think the equivalent risk is 6%, then they're below the IRR, and they would go ahead. And if they thought the equivalent risk was, 7.9%, then they would not go with the improvement to their furniture company. They would actually go with some external investment. Okay, so pretty easy. It's just sort of an increment in the analysis above what we had done earlier. We were kind of just eyeballing where the break-even point, the crossover point was, and now we have this additional capability where we can pinpoint it. The problem is that depending on the numbers you feed in, you can get more than one IRR, and we'll talk about that later. There's something called the modified IRR, which addresses that issue. As I just mentioned, it's possible to have two IRR values for a given NPV equation. And I have an example of that here. This table is the cash flow for a particular investment of $10,000. Then you have these cash flows, and then there's a negative out here. And it turns out there's two IRRs, 5.07 and 82.43%. So this number here is kind of dragging things out to this percentage, much higher percentage. And the Excel IRR function asks you to make a guess in terms of what the value would be, the IRR would be. So depending on your guess, you're going to get either this one or you're going to get that one, this larger value here. And it's basically problematic that you're not sure which way to go here. Especially these are so far apart. What I did also, and I'll show you this on the next slide, I wrote out the NPV equation. So you have the negative investment. I divided by 1,000. I divided all these numbers by 1,000. So you get the negative here, and then you have the discounted present value of these cash flows. You notice the last one's negative. And if you graph this using a graphing function, which I did, you'll see that the function crosses the horizontal axis, which represents I, the interest, in two different places. So let's have a look at that on the next slide. Yeah, so here's the graph I mentioned of the NPV equation, and it has two intersection points. One is around 0.5, exactly, what was it, 5.07 or 0.00507 in terms of decimals. And then there was one here over 80%, and you can see that intersection here. So two different, and there's no reason that it has to be only two. If you did the cash flows for like more periods, maybe if it was monthly and you did it over 10 years, and there's a lot of up and down in terms of the cash flows, this equation could very well be crossing the line and coming back again multiple times, and you would have multiple intersections here. So again, the vertical axis is the NPV, and the horizontal axis is I. When comparing mutually exclusive projects, the project with the highest IRR may not be the project with the highest NPV. In such situations, the NPV approach is generally preferred because it measures the actual increase in value created by the investment. The conflict between IRR and NPV approaches is often explained in terms of their different reinvestment assumptions. The key word here is assumptions. These are not necessarily things that have to happen, but they're assumptions that typically happen. The NPV approach implicitly assumes that intermediate cash net flows, in other words, the net cash flows during the life of the project, can be reinvested at the cost of capital or required rate of return. The IRR approach implicitly assumes the intermediate net cash flows can be reinvested at the project's own internal rate of return. Issues, and that's may not be realistic, that's the problem. Issues with the IRR approach are well explained in this article. I'll give you a reference to this from McKinsey and Company. They have an example where two projects, project A and B, have the same IRR, but one project, I think it was the second project, B, or maybe it was A, it doesn't matter, but one of the two projects had the possibility of investing on a follow-up project that paid a very high rate of return, where the other project did not. So even though they had the same IRRs, the potential for reinvesting the money was quite different between the two. So I'll give you a link to this article. I think you need to subscribe. It's a free subscription to access the article, but I did it myself just a little bit ago, and I was able to access it. If the IRR is very large, this assumption may be unrealistic. For example, a project with an IRR of 40% implicitly assumes that internal cash flows can continue earning 40% elsewhere. In practice, opportunities with such high returns are often unavailable. That's what I just mentioned. As a result, the IRR approach can exaggerate the attractiveness of certain projects, especially projects with large early cash flows. Then concerning this reinvestment assumption, I have a note here. The commonly stated reinvestment assumptions associated with NPV and IRR are somewhat misleading if interpreted literally. Neither NPV nor IRR formula explicitly reinvest in term cash flows during the computation. Rather, the assumptions arise from economic interpretations of the methods, particularly when interpreting IRR as a compound rate of return over the life of a project. The primary advantage of the NPV method is that it directly measures the increase in value created by an investment using a market-based required rate of return. Suppose a company must choose between the following two projects and the cost of capital is 10%. So the projects are shown here, project A and B, over 2 years. They both have an initial investment of $1,000, and then these are the net cash flows over the 2 years. If we do the calculations, project A has a higher IRR than B, and B has a higher NPV than A. So although project A has a higher IRR, project B creates more value because it has a higher NPV. The IRR method favors project A, obviously, since it has a higher number there, because of its extremely high percentage return over a short period, while the NPV method recognizes project B ultimately generates more wealth in the present value terms. For this reason, when mutually exclusive projects conflict, financial theory generally recommends choosing the project with the higher NPV rather than the higher IRR. So we have a variation on the IRR. It's called the modified internal rate of return. It's a measure of an investment's attractiveness, just like the IRR, but it addresses some issues with the IRR, which I'll talk about. It is used in capital budgeting to rank alternative investments of equal size. The MIRR is a modified version of the IRR concept, and as such aims to resolve some problems with the IRR. Conceptually, the MIRR simplifies a complex series of cash flows into a single investment life cycle. So we'll just get one number out of our calculations. It calculates the compound annual growth rate necessary to turn the total present value of a project's cost into the total future value of its returns. So the formula is a bit complicated. Let's go through this slowly. There's different parts to it, and then we get a final solution, this thing Z down here. So we first determine the future value of all periods with positive cash flows using the cost of reinvestment. In other words, how much money you can make by reinvesting these cash flows. And that's the value X, which is down here. So you notice it's the I is the cost of reinvestment, or the value you can get from reinvesting. And then it's from that end of the period to the end of the project. So that's why you have N minus T sub K here. T sub K is the end of the period. So that's our X. And then Y relates to the negative cash flows. We want to compute the cost of those if we had to finance them at a rate J, and that was discounted back to the start of the project. So that's what this is here, this summation here. And so once we have these two, the MIR, the rate of return at which the value Y accumulates to the value X, so by the end of the project. So that's what you have here. And you notice there's a minus sign because Y is negative, so that makes this positive. And then this would be how much you accumulate from your Y to the end of the project, compounding each of the end periods, and the rate is Z. So you're looking for Z. That's what the MIRR is. And then I'm just showing here on this line here how to solve for it. We divided the Y, minus Y into X, and then we took the nth root of this, which would be a positive number, since X is positive and Y is negative, and then this negative makes this positive, and then you just subtract the 1 and you get this number for your MIRR. Okay, so a little bit complicated. You don't need to memorize the steps in deriving this. There's routines or functions that'll compute this for you. You basically need to have the project, the net cash flows for the project, and then you need the cost of reinvesting, how much money you can make by reinvesting the positive cash flows, and how much it would cost you in terms of interest to finance the net negative cash flows. So you need I, J to compute X and Y down here, and of course you need the cash flow numbers and the number of periods and the timing of the end of the periods. These T, we talked about these before, and then you plug it into this formula. Okay, so let's look at the advantages or the benefits of using MIRR in the next slide. The MIRR is used in a manner similar to the IRR. If the MIRR for a project is greater than the cost of capital, then we go forward with the project. Otherwise, we don't go forward. When comparing several projects, the projects with the highest MIRR is preferred. Further, the MIRR can be used to rank projects of different sizes. So that's just by whatever that value is, we can rank them. So it might be that a company can afford more than just one. It might not be a decision between project A or B. It might be that you have 5 projects and you can afford 2 of them, and then this would help you rank the projects, and then you might pick the top 2 if you want to use MIRR. Unlike the IRR, there is only one MIRR for a given project. So we recall we saw that graph in the example where we had the IRR crossing the horizontal axis twice. So that doesn't happen with the MIRR. Further, and as noted in the definitions in the previous slide, the MIRR computation allows one to use a reinvestment rate of return I that is different from the MIRR itself. So that's yet another advantage of the MIRR over the IRR. On this slide, I have an example of the computation of an MIRR function for a project. At the bottom here, I have the cash flows, the net cash flows for the project. And the initial investment is $25,000. The first year, the net cash flow is negative, and then it's positive for the next 4 years. So we compute X, shown here. We have the 5,000, this 5,000 here, that compounds for 3 years, right? This year, and this year. And we are assuming the reinvestment rate is 0.04. Then this would compound for 2 years, 1 year, and then of course this is at the very end of the project. There's no compounding, you just add that in. So you get this number here. Then you have one negative cash flow, and you want to get the present value at the time 0. So you have to compute that back one interval. And the rate there is assumed to be, the cost of financing would be 0.05. So notice these two don't have to be the same. And then we have the negative 25,000 at the very beginning. So you compute the positive cash flows to the end and the negative cash flows to the beginning. And then you just plug it into the formula. You remember this was the minus x over y, which is negative, and you can see here how the negatives cancel. Take the 5th root of that, subtract 1, and you can do this on a lot of calculators if you wanted to, and you get the MIRR. And you can cross-check this or double-check it with the Microsoft Excel MIRR function, and that gives you this result. And if you want to actually get the syntax for that, you can just just do a web search on modified IRR in Excel, and at least for me, that came, the Microsoft page came up first. Using the Excel IRR function, we get a IRR of 23.99. So we see we get a different value here. And if you go to the Wikipedia article, again, I think you need to do modified IRR in Wikipedia, and that'll bring up yet another explanation as well as another example to have a look at. Okay, so that's it for the IRR and MIRR. I have a couple other topics to complete this lesson, and I'll get to that on the next slide. The payback period and the discounted payback period are two additional techniques used to evaluate investment projects. The payback period approach entails a calculation of the time duration required to recover the cost of an initial investment. The shorter the time, the better the investment. And then the discounted payback period approach is similar, except that one uses the discounted values of the cash flows back to the time zero of the project. Then I have some definitions here, very similar to what I just said, so I'm not going to read them. You may want to pause the video if you want to study these, but these are from Investopedia, and as I say, they're pretty much what I just said. The only small variation or argument I would have is in the second definition, the Investopedia says a discounted payback period gives the number of years it takes to break even. And I would have just said maybe the length of time, because you may be evaluating the project on a semi-annual or quarterly basis, in which case you might say the number of quarters or the number of half years. Other than that, it's pretty much what I just said. So let's have a deeper look at these two. On this slide, I have an analysis based on DPP, discounted payback period, where we have two projects, A and B, and I have their cash flows here. This is top tables for project A. You can see the cash flows in the second row. And then the bottom table is for project B, and it has the cash flows. You notice both projects have an initial investment of $155,000. And the DPP analysis entails when the accumulated discounted cash flows first become positive. So we'll do that computation for each project. First we do the discounted cash flows. So we need to take each one of these cash flows and compute its present value at time zero based on, in our case, 2.5% cost of capital. That's the assumption. So we do that computation, and then we just add these numbers as we go along. So we have the negative 155,000 first, then we add 19,512 to that, and we get this. Then we add the 1936, we get this number. So we keep adding. Eventually we're going to get positive, and that happens at the end of year 6. If we do the same thing for project B, we don't become positive in terms of our accumulated discounted cash flows until year 7. So with respect to DPP analysis, we would go with project A, since it has a break even, or it breaks into positive territory 1 year sooner than project B. We have one more measure in this lesson concerning the profitability between multiple projects, and that's called the profitability index. It's the ratio of payoff to investment for a proposed project. It is useful for ranking projects because it allows one to quantify the amount of value created per unit of investment. More precisely, the probability index is shown here. So you take the NPV of the positive net cash flows for a project. That's this here, and that's what that PNCF stands for, positive net cash flow. And then we divide that by the NPV of the negative net cash flows, negative net cash flows. That's what this acronym is here. And then the quotient is the what's called the PI, the probability index. And we make this we make this positive here. So I probably could have just put a negative sign here to make this thing positive. Then I have a remark. Some, perhaps most sources use an alternative definition of PI where the denominator only includes the initial investment and the numerator is the sum of the present values of all other cash flows, positive and negative. And if you want to see that definition in detail, go to Investopedia and then look on their probability index. And they have an example also using that alternate definition. So I have one example here. We use the example from the previous slide. We do project A computation first, and you notice that we had that initial investment of 155, and I made that a positive number. And then we did the NPV for all the positive net cash flows, which we have on the top here. So for this example, we only had one negative net cash flow, and that was the initial investment. And then we do the same thing for B, and we get and then we divide and we get the two different PIs, and A is a little bit higher. So again, we choose project A because it has a higher PI. Okay, so that was it for capital budgeting. It's also it for this lesson and for the two lessons we had in capital budgeting. I do have some exercises, so I'll do that in the next lesson, so stay tuned for that.